Before we begin, let's step into a store to buy some apples. Let's say we need 24 apples. When we collect them, we get them in 2 boxes, with 1 dozen or 12 apples in each box. Here, dozen is a unit of measurement that helps us simplify and state a large quantity, like 12. When scientists were working with elements and compounds, they felt the need to have a unit of measurement to count entities at the microscopic level. Thus, the SI base unit, mole, was introduced. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, electrons, or protons. Note that 1 mole of a substance always contains the same number of entities, irrespective of the identity and kind of the substance. The term mole is used to count particles such as atoms, molecules, ions, electrons, and protons. Hence, we must indicate the nature of the particle under observation. For example, saying 1 mole of hydrogen would be incorrect. We need to specify the entity we are referring to. That is, hydrogen atoms or hydrogen molecules. Thus, the correct term would be 1 mole of hydrogen atoms or 1 mole of hydrogen molecules. But what is the value of a mole? Let's find out. We know that a carbon-12 atom is used as a base to calculate the atomic mass of elements. Hence, scientists used carbon as the base to determine the value of 1 mole. They used a mass spectrometer to determine the mass of a carbon-12 atom and found it to be 1.992648 multiplied by 10 raised to -23 gram. They then divided 12 gram moles of carbon-12 by the mass of carbon-12 and obtained 6.0221367 multiplied by 10 raised to 23, which is the number of atoms in 1 mole or 12 gram of carbon. This is the value of 1 mole and is known as Avogadro's number or Avogadro's constant, in the honor of Amedeo Avogadro, and is usually represented as Na. Avogadro's number or Avogadro's constant is defined as the number of elementary entities, atoms or molecules or ions in 1 mole of a substance. Thus, we can say that 1 mole of water molecules contains 6.022 multiplied by 10 raised to 23 water molecules. Having found the number of moles in a substance, we can determine the mass of a mole, also known as molar mass. Molar mass is the mass of 1 mole of substance expressed in grams. The molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Let's determine the molar mass of water. We know that water comprises 2 hydrogen atoms and 1 oxygen atom. We can obtain the atomic masses of hydrogen and oxygen from the periodic table. The atomic mass of hydrogen is 1.00794 and the atomic mass of oxygen is 15.9994. If we add the atomic masses of 2 hydrogen atoms and 1 oxygen atom, we get the molar mass of water as 18.02 gram. We've learnt that molecular mass of a substance can be obtained by adding the atomic masses of all the atoms present in one molecule of the substance, and the molar mass is numerically equivalent to the atomic or molecular or formular mass in U. Thus, we can conclude that the mass of 1 mole of any substance is equal to its molecular mass. We have seen how to determine the number of entities present in a substance. At times, scientists also require to know the percentage of elements present in a compound. This information helps to determine the purity of the chemical compound under observation. The percentage composition of elements or constituent in a compound is the number of parts by mass of that element or constituent present in 100 parts by molar mass of the compound. Let's look at an example. We know that the molar mass of water is 18.02 grams. Based on this, we can calculate the percentage of hydrogen and oxygen as shown. Thus, the percentage of oxygen and hydrogen in water is 88.79 and 11.18 respectively. Molar mass and percentage composition helps us understand the quantitative data associated with a chemical compound. But how does one arrive at the chemical formula of a compound? In other words, how did scientists obtain the formula H2O? The chemical formula of a compound is derived from two parts, the empirical formula and the molecular formula. The empirical formula is defined as the formula which gives the simplest whole number ratio of the different atoms present in one molecule of the compound. For example, the empirical formula of water is H2O. This indicates that in water, 2 hydrogen atoms are present for each oxygen atom. Similarly, the empirical formula of glucose is CH2O. This indicates that there is 1 carbon atom for every 2 hydrogen and 1 oxygen atoms. Note that the empirical formula only indicates the atomic ratio of the elements present in one molecule of the compound. Now, let's look at molecular formula. The molecular formula is defined as the formula which gives the actual number of atoms of various elements present in one molecule of a compound. In case of water, the molecular formula is H2O, same as the empirical formula, because one molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. In case of glucose, the molecular formula is C6H12O6. This means that one molecule of glucose has 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms. The molecular formula of a compound is an integral multiple of the empirical formula. The equation can be illustrated as shown. The value of N can be obtained by dividing the molecular mass with the empirical formula mass. The empirical formula mass is the sum of the atomic masses of the atoms present in the element. Let's say we have a compound CH2. The empirical formula of the compound will be the sum of the atomic masses of 1 carbon atom and 2 hydrogen atoms, which is 14 gram mole. Now, let's say that we know the molecular mass of the compound is 28 gram mole. Thus, 28 divided by 14 gives us 2. Then, we multiply 2 by the empirical formula and get C2H4. We've learnt how to calculate molar mass, percentage composition, empirical formula and molecular formula. But when do we apply these calculations in chemistry? Let's say we have conducted an experiment and obtained a compound that has 29.11% sodium, 40.51% sulfur, and 30.38% oxygen. And the molar mass of the compound is 158.1 gram. How can we determine the empirical and molecular formula of this compound? First, we have to convert the mass percent to gram. As we have the values in mass percent, we can consider the value of the sample as 100 gram and then convert the percent values to gram. Next, we have to determine the number of moles in each element. Divide the mass of element in gram with the atomic mass of the element. The atomic masses of various elements can be identified from the periodic table. Therefore, the relative atomic mass of sodium, sulfur, and oxygen are 23, 32.1, and 16 respectively. On substituting the values in the equation, we get the number of moles for each element as 1.266 and 1.897. Next, calculate the simplest molar ratio. Divide the moles of various elements present in the compound by the smallest quotient obtained as a result. This gives the simplest molar ratio as 1:1:1.5. If the ratios are not whole numbers, then multiply the number with suitable integer to convert them into whole numbers. In this case, if we multiply all values by 2, we get all ratios as whole numbers. That is, 2:2:3. Write the empirical formula by mentioning the numbers after writing the symbols of respective elements. First, write the element symbols next to each other. Then, insert the obtained numerical value of the simplest whole number ratio at the lower right-hand corner of each symbol. This gives the empirical formula of the compound. That is, Na2S2O3. Now, let's see the steps to determine the molecular formula. First, calculate the empirical formula mass. The empirical formula mass can be obtained by adding the atomic masses of all the atoms present in the empirical formula, which is 158.1 gram. Now, divide the molar mass by the empirical formula mass to identify the value of N, which we get as 1. Then, molecular formula of a compound can be determined by multiplying empirical formula of the compound with N. In this case, the molecular formula will be the same as the empirical formula. That is, Na2S2O3.